ครับ Good afternoon, everyone. Do you have any question before the class? So I hope you can see the screen. I already shared the slide. Our today's topic is the kinetics of particles. Before this, we spent most of our time in the previous weeks to study about the kinematics. In the kinematics chapters, we only consider the motion of the particle in the different type of coordinate, but we never talk about the force or the torque that affect the motion. But for today, we are talking about the force that affect the motion and the relationship between the force and the motion. The relationship between the torque and the motion are what we are talking about in the kinetics. But for particles, as the particle don't have the dimension, so we mainly focus on the relationship between the force and the motion of particle in this chapter. And today's topics, we are going to introduce the idea of the equation of motion. What is the equation of motion of a system? And after that, we will have a very short review about the coordinate system that we had already studied in the previous week. We will check the summary of the different coordinate system. We have the acceleration in the normal, in the tangential direction, in the radial direction, in the transverse direction, in the XY direction. Before this, we consider the velocity, the acceleration in the different direction, which correspond to the different coordinates. But today, in the topics of the kinematics, we need to relate the force in the different direction to the acceleration in the different direction to solve the problem. So we will review the coordinate system, and we have some example, and we're gonna relate the force in the different direction to the acceleration in the correspond direction to solve the different dynamics problem in the example. Talking about the equation of motion, the principle of the equation of motion is come from the Newton's second law of motion. And we know that for the particle, if we are not considering the dimension of particle, we are not talking about the rotation effect. We only study the translation of the particle. So the form of the Newton's second law of motion that we are talking about in today's class is the summation F equal to ma. And in this equation is written in the vector form, but in this example, it's a rectilinear motion in one directional. So yes, the governing equation is summation F x equal to ma x in the x direction. And we may set the x direction to be positive to the right-hand side and start from the equilibrium point of the spring, x equal to 0 at the spring equilibrium, and x going to be positive in the right hand side. And in this system, we have a mass, the block with mass m, that we put on a smooth surface and neglect the friction between the box and the floor. And we apply the mass, no, we apply the force as a function of time. Force can be vary against time, don't need to be a constant force. And in this system, we have a spring in the system, and we have a damper in the system. And if we write down the free body diagram of the mass m, the mass m has the mg at the center of mass, and the connection between the floor and the mass, we have the normal force, and we have the force, which is the boundary force that apply on the surface of the mass. You can see some, like, I write down the vector which represent force in this free body diagram, but you can see different type of vector that I draw in the diagram. For the mg, the arrow stop at the center of gravity and show the point that the force seems to apply to an object. For the normal force, in the real situation, the normal force apply on the surface of the box. So the arrow stop here. For the force also, we cannot apply force in the center of the mass, but we can apply the force to the surface of an object. So it applies here. In the same way, we have the spring force, and we have the force from the damper. If the box is going into the positive x direction, if the force is going to the positive x direction, the spring force will be on the opposite side of the positive x direction. So if we assume the box going in the positive x direction, the spring force will go into the left-hand side direction or the negative direction with the magnitude of kx, which is the spring constant multiplied by the displacement x. In this case, the displacement x we measure from the equilibrium position when x equal to 0. For the damping force, the damper, in general, the role of the damper is a kind of energy dissipator. And we have energy in the system, and we have the friction in the fluid, and we dissipate the energy through the friction in the fluid. And the damping force has the linear relationship with the velocity. The damping force has the linear relationship with the velocity. And the constant is the damping coefficient for the spring, K is the spring stiffness. And for the mass, or the inertia property, you can see for the direction here. In this case, we assume the x to be positive in the right-hand side direction, and also the velocity, and also the second time derivative. It's gonna be positive in the right-hand side direction. So if the mass move to the right-hand side or positive x direction, the force will be in the left-hand side or the negative direction. In the same way, if the mass has positive velocity to the right-hand side, the force generated by the damper is on the opposite direction to the velocity. So it's point toward the left-hand side direction. This is still true. This is still true. Now you assume x dot and x dot dot to be positive to the right-hand side, but in some case that mass going to the left-hand side of the reference point, in some case mass move to somewhere on the left-hand side of the reference point. At that moment, the x value or the position value will be negative. The position value will be negative, which means x is less than 0. If x is less than 0, and it multiplied by the spring constant K, the force generated by the spring, and we assume the direction to the left-hand side, but the magnitude will be negative, which means in the physical phenomena, it means the direction of the arrow is wrong. I mean, the direction of the real force should be on the opposite direction to the arrow. If the value here is less than 0, but we point it to the left-hand side, so it means in the real meaning, the force should be on the right-hand side, which is makes sense, right? X equal to 0 at the spring equilibrium. If the mass is on the right-hand side of the spring, X is positive, and the force from the spring will point toward the left-hand side direction. But if the mass is on the left-hand side of the equilibrium and x is less than 0, if x is less than 0, the product of kx also less than 0, and the arrow here, the real force from the spring should be on the opposite direction to the arrow here, which means the spring force should be to the right-hand side direction if x less than 0. Also for the velocity, if the velocity is positive to the right-hand side, the damping force will point to the left-hand side. But if x dot or the velocity, is point to the left-hand side, it means x dot less than 0. If x dot less than 0, the product of Cx dot less than 0, the force created by the damper should be point to the right-hand side. Please keep in mind that the damping force is position independent. It only depends on the velocity. No matter the box will be on the right-hand side or on the left-hand side, the position of the box is not important for the damping force. Just the direction of the velocity is important for the damping force. If the velocity is positive to the right-hand side, the damping force will resist the motion. The damping force will resist the motion. If the velocity is negative to the right-hand side, the damping force also resists the motion because the damping force will try to push to the right-hand side if the velocity is to the left-hand side. So this is the idea. And the governing equation is summation fx equal to the max. We also have the summation fy equal to may. But in the y direction, we have the normal force in the upward direction and positive. And we have mg in the negative direction. Why the force is opposite side? Can you explain again? Okay, we have one question in the chat. I just see why the force is opposite side. Why the force is opposite side? Okay. We may begin with the spring. First, if the spring is in equilibrium and x equal to 0, the spring force is 0. If you move the box and the spring is stretching, if you move the box to the position, the positive position, if you move the box to the positive position, can you tell me what is the direction of the spring force that apply on the surface of the box? The spring force will go in the negative direction. The position x is positive to the right-hand side, but the spring force is opposite to the displacement. In the same way, if the box moves to the left-hand side and the spring is compressed, the spring force will push toward the right-hand side. This is for the spring force. For the damping, for the damper, by the principle of the damper, it also resists the motion, but it resists the velocity. So for the spring, we can draw the picture in the static case to explain why the spring force is opposite to the direction. But for the damping, maybe we should draw something moving. But please keep in mind that if the object is moving to the right-hand side with the positive velocity, if the spring is moving to the right-hand side with the positive velocity, the force from the damper will resist the motion and go to the left-hand side. On another way, if the spring is moving to the left-hand side, if the spring is moving to the left-hand side, which means x dot is less than 0, the spring for the damping force will resist the motion and apply to the right-hand side, no matter the position is positive or negative. If the velocity is negative, the force from the damper will be on the right-hand side or on the positive direction. It's better. I mean, is it answer your question? Okay. Let me see. Okay, for the vertical direction, summation Fy is equal to MAy. So the normal force in the upward direction is positive y. But the mg is in the negative y direction and is equal to the mass multiplied by the acceleration in y direction. But we know that the box is on the floor and have 0 acceleration in the y direction. So we have one relationship, the normal force is equal to the mg. For the horizontal motion, if we consider this free body diagram, and consider the horizontal force, we have the force which can be a constant force or a force that can change against time. The force is positive to the right-hand side direction. And the spring force resists the motion. The spring force, we put the negative sign here, the minus sign here, because if x is positive, the force will negative. And for the damping force, the damping force has one coefficient and multiplied by the velocity. We also have the negative sign here to indicate that if x dot is positive, the force will be in the negative side direction. And the force in the horizontal direction have only the external force, the spring force, and the force from the damper. And it needs to equal to MA in the x direction. Acceleration in the x direction. Is the second time derivative of the position. So from this equation, we can rearrange the equation to be m x dot plus cx dot plus kx equal to the external force. And this is the equation of motion of this system, of this second order system. Equation of motion of this second order system. The equation of motion relates the force or the effort that we apply to the system. To the flow, and the time derivative of the flow. Effort is the force, flow is the motion of the system. We can have the time derivative of the flow and the time integral of the flow. Flow and displacement, flow and displacement. So the equation of motion relate the effort and the flow and the time derivative of the flow and also the displacement. And the property of the system here, as we mentioned, we have the inertia. We have the stiffness. And we have the damping. The inertia, the stiffness, and the damping, these three terms, we can call it mechanical impedance. Mechanical impedance. To make it simple, the simple definition of the mechanical impedance is how much the system resists the motion. If the system has big inertia, is heavy, it's not easy to move by the same amount of the applied force. If the system has a big stiffness, K, you may talking about the big spring with a large stiffness. It's not easy to compress a big spring with large stiffness. If you're talking about the damping, if the damper has a big damping coefficient, it's not easy to change the velocity of that damper. So the mechanical impedance, the property of the inertia, damping, and stiffness is the thing that resists the motion. For our robot application, if we want to develop the system, the robot system that interact with human, if we want to develop system that interact with human, before this, for the industrial robot, the requirement for the industrial robot is we just want the robot to carry a heavy object in the factory. The motor to drive the robot, the motor can create some amount of torque by the motor. But if we want the motor to carry a big load, the direct solution is we just add the gearbox to the motor so that the motor can have a bigger torque to drive the system, to carry the load. But if we add the gearbox to the motor, we are adding the inertia to the motor. If you may, the motor has the moment of inertia, and if you interest in this, you may find some external source to read. But what I want to say is, if the motor has the moment of inertia of the rotor, it will be multiplied by the square of the gear ratio, and we can get the output inertia of the motor. For the industrial robot, if we want to obtain the high torque, we use a high gear reduction ratio to the motor. Of course, we can get the amount of torque we receive from the motor and gearbox, but the undesired property is the large inertia of the motor and gearbox. It can be good if the robot just moves by itself in the separate environment, but if the robot need to interact with the environment or need to interact with the human, the high inertia is undesired effect, because if the robot hit with something, it can create a big damage. So the mechanical impedance for the human-robot interaction, we may prefer in some time, if we want the robot to feel safe and smooth, we may want to reduce the mechanical impedance of the system. How can we reduce the inertia? How can we reduce the friction? And sometimes we can adjust the stiffness of the actuator so that when it interacts with the human, we can feel it safe. If we want it to be like stiff, we can adjust the stiffness. If we want it to be soft, we can reduce the stiffness. Yeah, this is the introduction to the mechanical impedance for the human-robot interaction. But it's still, it's not about, it's not in the textbook. Yeah, it's just introduction to the equation of motion. But the equation of motion is the equation that relates the force or the effort to the flow or the displacement, the velocity, the acceleration of the system. And I hope you still remember in our previous weeks, for the rectilinear motion in one direction, we have the summation F equal to MA. If we are talking about the curvilinear motion in 2D, if we use the rectangular coordinate in the XY coordinate, the Newton's second laws of motion can be applied to that individual direction of coordinate. The summation Fx equal to Max and summation Fy equal to May. You may already familiar with this from our physics class when you study the mechanics. But what news in our class, we derive the normal acceleration and tangential acceleration, right? The Newton's second law of motion is still true for the nt or the normal tangential coordinate, the summation of force in the normal direction is equal to mass multiplied by the acceleration in the normal direction. For the tangential direction, also, the summation of force in the tangential direction is equal to ma in the tangential direction. The normal acceleration is the acceleration that perpendicular to the direction of the velocity. It's v squared per r. Velocity squared divided by the radius of curvature. This is the normal acceleration. For the tangential direction, because for the nt coordinate, the velocity is only on the tangent direction. So the rate of change of the magnitude of the velocity, the rate of change of the speed is equal to the tangential acceleration. It's straightforwardly. For the polar coordinate, this is also easy to understand. The radial direction is the second time derivative of the change in the radius. The second time derivative of the change in the radius. And we need to include the centrifugal acceleration. The centrifugal acceleration, actually, these two terms are the same in amount. When the radius is constant, when we consider the radius as a constant at that time, the acceleration to the center of the rotation is equal to the radius multiplied by the theta dot square, or equal to the v square per r at that moment. So the radial acceleration is r dot dot to the outward direction. And the centrifugal acceleration point to the center or the origin. So it has the negative sign. Of course, for the nt coordinate, we point the positive n direction to the center of the part. But for the polar coordinate, we point the positive r direction outward from the origin. So this is why rho beta dot square is positive, but the r theta dot square is negative. It's just because we set the positive and negative direction of the axis in the different direction. For the transverse or the transverse acceleration, the r theta dot dot is very easy to understand, right? It's r alpha. The acceleration, the linear acceleration at the point on the rim of a disk is equal to the radius multiplied by the angular acceleration. But for the second term, this is the effect of the change in the radius. It also affects the acceleration in the theta direction. So this is just the review, but we already provide the derivation in our previous class. So if you still not understand how can we obtain this, please review our record class, but today we put this summary because we are going to use this knowledge in today. So let's begin with the first simple problem. In this problem, the explanation is we have a man and a cart on a slope. We have a man and a cart on a slope, and the cart has a smooth wheel on a slope, and we're gonna neglect the friction between the floor and the cart because we have the wheel here, and we have the angle that indicate the slope. And a small complexity of this problem is, we have a roof here, and the roof go through the pulley, the two pulley. And what they give in this problem, we know the slope. We know the slope 15 degrees. And we know the mass of the man, including the cart, of 100 kilograms. And the man pulled the roof with the force of 250 Newton. Maybe the force here, the force at this point, the force that the man pulled the cart, and the force that, the force T is 250 Newton. The force T, 250 Newton. So if we draw, in this problem, what we need to find, the acceleration. We need to find the acceleration. I'm gonna put the reference coordinate in the incline. On the incline slope, we have the x direction and the y direction like this. We know that we have the zero acceleration in the y direction because the cart run on the slope, but we have the linear acceleration on the plane of the slope, and we need to find the acceleration. We should begin with drawing the free body diagram of the cart, include the man. And if we remove the floor, we have the x coordinate and we have the y coordinate. And we know the angle, theta. The force that support the cart is the normal force from the slope, and the cart itself and the man has mg. And if we cut the cart from this line, it seems like we need to have the force that represent the boundary force when we cut the cord from the cable. Of course, at this point, we know that if we cut it, we have the cable tension T that pull the cord upward. But how about the force here at the boundary? How about this force here at the boundary? Let's see the pulley here. Let's see the pulley here. And I'm gonna assume the tension in the cable here is equal to T1, okay? And at this point, it's gonna be T2. And here also T2, because it's in the same cable. And after the pulley, we're gonna have T3. If we check the pulley, the first pulley here, we have T1 and we have T2. And the center of the pulley is point O1. O1 is here. And for the second pulley, we have the point O2 at the center of the pulley. And the O2 is the center of the pulley. And of course, we have the T2. And we have T3 to the pulley. I want you to check the first pulley here. I want you to check the first pulley. If we do the summation of moment about point O1, it should equal to the moment of inertia of the pulley multiplied by the angular acceleration of the pulley. We may assume the counterclockwise direction to be positive. Of course, the pulley has the radius. We can assume the radius of the pulley R. The summation of moment about point O1 when the counterclockwise direction is positive will be T1 multiplied by the radius, which is positive to the counterclockwise direction, and T2 multiplied by the R is negative because it's on the clockwise direction. And it needs to equal to the moment of inertia of the pulley multiplied by the angular acceleration. But in this case, they negate the mass of the pulley. So the moment of the inertia of the pulley also zero with some angular acceleration. I write this free body diagram and this equation of motion just to show you that when we ignore the mass of pulley, T1 will equal to T2. When we ignore the mass of the pulley, the tension of the cable in and out will equal T1 will equal to T2 because the moment of inertia of the pulley is zero. Okay, for the pulley number 2, what happened here? We should have T2, T3, and T4 here, T4 on the center. T4 on the center. Yeah, we are not going to repeat the summation of moment here. It's in the same analysis, but at least if we do the summation of moment, what we are going to obtain is T2 is equal to T3. But if we consider the direction X and Y of the pulley, and if we do summation of force in the X direction of the pulley, if we do the summation of force in the X direction of the pulley, it needs to equal to the mass of the pulley multiplied by the acceleration of the pulley. Summation of force is T2 plus T3 in the positive X direction, and subtract by T4 in the negative X direction. And it will equal to the mass of the pulley multiplied by the acceleration of the pulley. Oh, okay. Thank you for the question. For the first pulley, yeah, this is my mistake. We may put T5 here. Yeah, this force can be T5 here. T5 gonna affect the force, but it's not gonna affect the moment about 0.01 because T5 pass through the center of the pulley or the 0.01. So if we have T5 or not have T5 to the first pulley, it's not affect the summation of the moment. It's not affect the summation of the moment. But if we want to know the magnitude of the T5 from the magnitude of T1 and T2, or if we want to know the magnitude of the T4 from the T2 and T3, we are writing the summation of force in this way. We can analyze in the same way to obtain the T5 or to obtain the T4. But we are not going to obtain the magnitude of T5 because it's not affect our motion. But we are going to derive the T4 because it has the boundary connection to our card. Okay, but thank you for your reminder. I mean, we need to have T5 on the first pulley here. We need to have T5 on the first pulley here in the free body diagram. Okay, come back to the summation of force for the pulley 2. We have the T2 and T3 in the positive direction, and we have T4 in the negative direction of the pulley. But the mass of the pulley is ignored. So what we get here, we just know that T4 equal to T2 plus T3. But if you check here, we have T that we know. T is provided by the problem, 250 Newton. T equal to T1, right? It's on the same roof. T is equal to T1. And when we ignore the mass of the pulley, we know that T1 equal to T2. So T1 and T2 is equal to T, the tension T. And if we consider the summation of moment about O2 of this pulley, you're gonna find that T2 is also equal to T3, because when we ignore the mass of the pulley, the moment of inertia is 0, and T2 is equal to T3, and yes, they are equal to T. But from this summation of force, you know that T4 is equal to T2 plus T3. You can simply write that T4 is equal to double of the tension T, double of the cable tension T. So if we switch back to the free body diagram, if we switch back to the free body diagram here, we have T at this point, and we have T4 that has the boundary connection to the card. And T4, the magnitude of T4 is equal to 2T. So if I write the summation of force in the y direction of the card, what we're gonna have is we're gonna have the minus mg phi theta plus n equal to 0, summation of force in the y direction of the card, minus mg psi, I'm sorry, minus mg cosine, minus mg cos theta plus n equal to 0. And if we find the summation of f in the x direction equal to max, what we're gonna have in the x direction is we have t and 2t, right? We have t plus 2t in the positive x direction. And for the mg, it will be minus mg sine theta. And it will equal to m a x. So yeah, now we know everything here, but max should equal to 3t subtract by mg psi theta. And we know the mass, we know the tension T, we know the gravitational acceleration, and we know the slope. So yes, we can compute the AX or the linear acceleration on the slope for this card. This is the first example. Do you have any question for the first example? Let me check. Fy. Let me check Fy. It should be minus mg psi. Okay. This is mg. Mg is going downward direction. And this is in the y direction with the theta. We have x and y direction and mg. And the theta here, the theta here is equal to the theta here. The theta here is equal to the theta here. So in y direction is the minus mg cosine theta, not the minus mg psi. Okay, we should have this example first before we have a break. In this problem, we have the mass of 60 kilogram and the mass of 20 kilogram. The mass of 60 kilogram is on a slope, and they provide the friction coefficient for the slope. They have the static friction coefficient and the kinetic friction coefficient. We should check first before we consider the motion of the system. In the system, they may ask us to calculate the acceleration. We need to calculate the acceleration. But if we check the force in the system and the tension that pull the box and the effect of the mg, if these two forces, the effect of these two forces, if we consider on the direction of the coordinate, if the effect of these two forces is less than the friction provided by the static friction, the system doesn't move. But if the effect of the tension and the mg in the direction here, if the effect of the tension and the mg is bigger than the static friction, if we calculate the acceleration, we need to consider the kinetic friction because the system is moving. So the problem provides two values of the friction coefficient. We need to check the static friction first to indicate whether the system is moving or not. if it moves, to obtain the value of the acceleration, we need to use the kinetic friction coefficient in our calculation. If we see the picture, we are not going to do any calculation first. But let us practice our engineering sense. In your opinion, if the system moves, do you think the mass B will going upward or downward? To use our engineering sense, if the cable has the tension T, the cable tension about the pulley, and we neglect the mass and the friction of the pulley. If the tension T here, at this point in the pulley, it also has the same tension T. If we neglect the mass and the moment of inertia of the pulley. And for this point, the tension in the pulley is T. With the same reason, the pulley is about, the cable is grouped about this lower pulley, and the tension in the pulley here should also be equal to T. Tension in the same pulley always be the same if we neglect the mass and the friction of the pulley. So we have the T in the upward direction, 2 of T in the upward direction. So here in the downward direction, it should be 2T. So by using the engineering sense, the 60 kilogram, we have mg in the downward direction. And of course, we have the theta here. And we have the X and Y direction. The mg in the X direction should be mg sine theta, right? In the X direction, here should be mg sine theta. And here should be mg cosine theta in the magnitude. So the mass here is 60 kilogram. The mass here is 60 kilogram. Sine theta, sine 30 degree is 0.5. So approximately, it seems like we have 30 kilogram that try to pull this thing upward. The tension need to fight with something about 30 kilograms. The tension need to fight with something about 30 kilograms. The block itself has 60 kilograms. But the direction of the mg side, it seems like we have the effect of the weight, about half of the weight in the x direction or the direction of the slope. So half of the weight, mg sine theta, is about 30 kilograms. The tension T here need to fight with 30 kilograms. And we still don't know who will win between 30 kilograms in the downward direction and T going upward direction. If we check the mass 20 kilograms, we have two of the tension in the upward direction. We have two of tension in the upward direction. And it needs to fight with mg. If we draw the free body diagram of B has mg and has 2t. If we draw the free body diagram of the A, we have X direction and has Y direction for A. And of course, we have mg. We have the normal force and the cable T. mg should be m1g. So my first question is, I want us to use our engineering sense to indicate whether the mass B will going upward or downward. mg of the first block is 60 kilograms multiplied by g, and sine 30 degrees is about 0.5. So it seems like we have the effect of 30 kilograms in the downward direction and fight with T. We have mg cosine 30 degrees and mg sine 30 degrees. Polawat, Polawat, you are thinking the mass B is going upward, right? Yeah, the answer is, the answer should be correct. Like we have, it seems like we have 300 kilogram. No, we have 60 kilogram and sine 30 degree. So the estimate force here, maybe something like 300 Newton, maybe. And the tension T need to fight with 300 Newton. But for the mass B, we have 2T to fight with the mass 20 kg multiplied by G, which is about 200 Newton. So 300 Newton fight with T, and 2T fight with 200 Newton by the approximation. If we need to process our calculation and need to assume the direction of the initial motion appropriately by using our engineering sense, the B need to go upward. The B need to go upward because 2T should be bigger than 200 Newton. Because 1T, the 2T should be bigger than 200 Newton. And 1T, exactly, it should less than 300 Newton. The number of the load here compared to 1T. And on this side, we have 2T in the upward and fight with just a small load, 200 Newton. So by the engineering sense, the mass A should going downward and the mass B should going upward. If we need to assume the motion to the system. But for this, we still didn't consider the effect of the friction. We still didn't consider the effect of the friction. If the system is going to go in this direction, the mass A going downward, the mass B going upward, what should be the direction of the friction? We still don't know which friction coefficient we are gonna use, but at least if we need to assume the direction of the friction, the direction of the friction force will resist the motion. The mass A seems to going downward, the slope. So the direction of friction should going upward to resist the motion. So what the problem give? The problem give mass M1 of the A equal to 60 kilogram. The mass of B equal to 20 kilogram. Mu static friction equal to 0.25. And the kinetic friction equal to 0.2. Here are what the problem give. And yeah, they neglect the pulley, mass, and friction. What we need to find is the acceleration of each body, acceleration of A, acceleration of B. So the solution, I hope you still remember the topic of the constraint particle motion. For the constraint particle motion is, hey, when we have two particles, A and B, connected by a loop, and the motion of the particle A affect the motion of the particle B. If we consider the length of the loop, let's check this picture first. This, if we let this as a YA, and we let this as YB, the length of the loop will equal to the length of the loop is equal to YA plus a constant here and plus a constant here and plus YB in the downward direction and YB in the upward direction. So the total length of the loop should equal to YA plus 2YB and plus a constant length of the loop. If we perform the first time derivative, we're gonna have YA dot plus 2YB dot. The time derivative of constant is equal to 0. And the total length of the loop also doesn't change. So the time derivative is equal to 0. So what we can write here is, at least we know that the magnitude of the acceleration, okay, if we want to do the acceleration, we obtain the second time derivative. At least from here, we know that the magnitude of the velocity, VA, should equal to 2 of VB. And the magnitude of the acceleration of the mass A should equal to the double of the acceleration of the mass B. It means anytime when A move and B move, the distance that the A move will be double of the distance that the B move. Y is equation equal to 0. Okay. Until here, I think you can follow this step. I think you still can follow this step. The total length of the loop, is measured from here to here. And the distance is YA. And we have this constant length C1 about the pulley, and we have the constant length C2 about the small pulley. And the length is depend on the distance YB in the downward direction and in the upward direction. And the constant C1 and C2 is not important. We just consider it as a constant length K. And the total length of the loop is equal to the summation of YA to YB and a constant length K. When we perform the first time derivative, we have YA dot to YB dot, and the time derivative of K is equal to 0. To answer your question, why the whole equation is equal to 0, is that the total length of the loop also doesn't change against time. When the time passes, the total length L still constant. So the L dot d by dt of the length is equal to 0. This is the answer to your question. Okay, from this page, at least from now, we know the relationship between the acceleration of the mass A and the mass B. We switch back to here. And which part we should consider first? Okay, let's see the mass B. Let's see the mass B first. Let's see the mass B first. Summation Fy equal to MAY. And the Y is positive in the upward direction of the mass B. The mass B has 2T force in the upward direction and have mg in the downward direction. And the acceleration should be AB in the upward direction, but we still don't know the magnitude of the acceleration. So when we arrange the equation, we can have MB and G plus AB. We know the relationship between the magnitude of acceleration AB and AA, right? The AA always double of AB. So in this step, I want to leave it in the terms of the tension in the cable. Tension in cable is equal to the mass of B divided by 2 and multiplied by G plus AA per 2. The important thing you need to do is this step. if you need to do the exam problem and you don't know how to derive until the end, at least I expect you to write down the governing equation and draw the free body diagram and put the correct form of the force and direction. The important equation is this one. For this equation, why I arrange in this way is because it's gonna useful for our solving, but you may still cannot see it now. But the correct step is to write down the equation 1 first, and maybe you just leave it, and you may transform it later when you see in which way you need to transform it. By the kinematic relationship, we have AA equal to 2AB. And what I did here is I just try to relate the tension T in the terms of the known parameter and the unknown acceleration of the mass A. This is the mass B. How about the mass A? The summation Fy of the mass A is here. The summation Fy is equal to the normal force in the upward direction and mg cosine theta in the downward direction need to equal to 0, because in the y direction it has no acceleration. So you know that the normal force is equal to the mass A multiplied by G and cosine theta. How about in the x direction of the mass A? Yeah, we expect that the mass A will go downward when the mass B is going upward. So the summation Fx in the downward direction of mass A has MA, G, and psi theta in the downward direction. And we have the T, or the tension in cable, that resists the motion. And we have the friction force that resists the motion also. And the friction force is mu multiplied by the normal force N. So the friction force will be mu and multiplied by N, or mg cosine theta. And this gonna equal to the mass A multiplied by the acceleration multiplied by the acceleration. We should use mu k. I think at this time, yeah, finally, in this problem, finally, we're gonna use mu k, but we can use mu k just only when we can confirm that the system is moving. But if the system doesn't move, it means if we provide the mu s, if we provide the mu s, and we can obtain the negative, how to say, wait a second. Okay. Finally, for this problem, when we need to obtain the correct acceleration, we're gonna use mu k. But at least we should make sure that if we use the mu s, we still can see the positive acceleration correspond to the direction that we presume. So for my computation, in the first step, I will try to use the mu equal to the static friction first. If we assume the mu equal to the static friction, and we still can see the positive acceleration in the direction that we presume, it means that the effect of the friction is less than the intention of the mg subtract by t. And if we still can see the positive acceleration when we assume the mu s, it means that, of course, when we use mu k, we still can see the positive direction. And the magnitude of the acceleration that corresponds to the mu k will be the exact value that we are going to solve. But before jumping to the mu k, we need to check the acceleration with the mu s first. If we see the negative value in this step, it means that the effect of the friction is bigger than the effect of the mg psi subtract by t. If we see the negative acceleration in this step, it means that the friction is dominant, the static friction is dominant, and the system doesn't move. If A is negative, it means the friction, the static friction, is dominant and doesn't move. But if A is positive in this step, can we just answer the A from this step? No, we cannot use the A in this step to answer, because if the system moves, the friction coefficient that we need to use must be the kinetic friction. So we check the static friction first. If we check the static friction, what we need to do here is we already compose the relationship between the tension and the acceleration of mass A. And in this equation, we know everything. We know MA, we know G, we know psi theta, and T is unknown. And AA is unknown. It seems like we have two equations with two unknown, T and AA. And we can solve for T and AA. Let me rewrite the equation 2 and 3 in the next page so that we can continue. I will write this and this in the next page. T tension is equal to the mass B divided by 2 and multiplied by G plus acceleration A divided by 2. This is equation 2. And equation 3 is MA G psi 30 degree T subtract by mu MA friction mu MA G cosine 30 degree is equal to MA and the acceleration A. And yes, this is equation 3. To solve these two equations is not difficult, right? You just put T into here. And okay, we have MA G psi 30 degree subtract by MB per 2 and G plus AA per 2 and minus mu MA G cosine 30 degree equal to MA and acceleration A. And we need to solve for A. And we are going to arrange the term that has A to the right hand side. So we have MA G. We have MA psi 30 degree subtract by MB per 2 and subtract by mu MA cosine 30 degree and everything multiplied by G. Is equal to MA plus MB per 4 of AA. As I mentioned, we firstly check the mu s static friction and to see if AA is positive or not. If AA is positive, it means that the effect of the mass subtracted by the cable tension is bigger than the static friction. And the system, the mass A is moving downward as we assume. And we can continue using the mu equal to the kinetic friction. But if not, if acceleration A is less than 0 in this step, it means that the system doesn't move because the effect of the static friction is dominant. So let's put the numerical value. The mass A, 60, psi 30, 0.5, and mass B, 20 per 2. And the mu, the static friction, is 0.25. Mass A 60, cosine 30 is 0.866. Okay, so let's check this term. What is the numerical value of this term? Yeah, I need your help to use the calculator. If anyone can compute this, please type in the chat. Okay, thank you, Hu, for computing. So this term, what we get here, the numerical value may be 7.01, right? And the 7.01 is more than 0, which means the acceleration A is more than 0. It means although here is static friction, is the big friction, although here we have the biggest possible value of friction, we still can get the positive acceleration. So the system is moving as we expect. In order to compute the correct acceleration of the mass A, the next step is to use the correct value of the friction coefficient. If we know it's moving, we should use the kinetic friction coefficient. So if we use the kinetic friction coefficient, again, we're gonna have the mass A 60 multiplied by psi 30 and MB 20 divided by 2. And the kinetic friction coefficient 0.2. multiplied by MA and multiplied by cosine 30. And multiplied by G equal to something here multiplied by acceleration. And yes, finally, you can solve for the acceleration. You can solve for the AA. And if we want to obtain the AB, you know this relationship, the AB will be the half in magnitude of the AA. And if you want to obtain the tension in the cable, you can use the equation 2 to solve for the tension in the cable. So yes, before going to the next example, we're gonna have a break for 10 minutes. And if you have questions, you can ask me by now.